Welcome for the week 11 session, live session for Smart Grid Basic Advanced Technologies. So, these are the deadlines for deadline is 11th. Yeah, it changes. This is 11th and this is 18th. Yes, in last class you said that you want to have an extra session. I think it will be official on most probably on 21st, Saturday 6 to 8 p.m. Hmm. Links for the recording are available on this YouTube channel. You can access. Let us begin the overview. So in this is second last week, and this is mainly related to the demonstration of DC microgrid. The first one was energy management in DC microgrid, then design of smart grid and a simple case study, and system analysis of AC/DC smart grid. In this, how to solve load flow equations. Power flow methods were explained for AC/DC hybrid microgrid. Last one is demonstration of grid connected DC microgrid. So starting with the first one, energy management in DC microgrid. So first of all, in DC microgrid, the control has one main important block, which is the power flow control block. It follows implements the power flow control strategy, and these are the different functions which it performs. The microgrid would like to reduce the peak demand so that the reliance on the main grid reduces. Then second one is a smooth transition between different modes. There are grid connected mode, island grid mode, and one is then effective control and management. Reduce stress on battery. Increase life cycle of storage such that so the strategy would try to keep the SOC within the range so that the life cycle of storage increases. Then it covers both the modes and also tries to keep unity power factor. This is the strategy which is implemented to ensure that there is reduced reliance on the grid, or the grid is not stressed during the peak hours. The microgrid should not withdraw take any power from the main grid during the peak hours. It can supply, but it should not absorb power. During off-peak hour, it can take power. We will see this strategy. So starting with this block. So first it is checked whether the grid is available or not. So if it is not available, that means it is isolated mode. This one is for isolated mode. Now in isolated mode grid is not available, so we have to see whether the generation from PV is greater than load. If it is greater than load and SOC is already more than 90%, that is battery is already charged, then battery is disconnected or it is not charged and PV moves to off MPPT and load is already supplied because generation is more than the load. But if SOC is less than 90%, then battery will be charged. PV will operate at maximum power point and load will be supplied. But if generation is less than load, so this path. So in that case, SOC is checked. If SOC is less than 30%, then move to this path. If SOC is not less than 30%, then battery will supply the load. So whatever maximum we can extract from PV will be extracted and the remaining load will be supplied by the battery. But if SOC is less than 30%, then we will have to curtail the load because PV is already less. So then as the SOC of battery reduces, you can curtail load. So here this is essential load and non-essential load. So this one is for isolated mode. Now if grid is available, then it is grid connected. In grid connected there are two modes, two possibilities. One is either peak hour mode or off peak hour mode. So then next thing we have to check is whether it is peak hour mode or off peak hour mode. If it is peak hour mode, yes, then again we have to check generation and load. So if generation is more than load, then SOC is checked. If SOC also more than 70%, then because it is peak and SOC is more than 70%, that means the battery can supply power to the grid, can help in reducing the peak requirement. The grid can absorb power, a battery will supply in this case. And PV operates at maximum power point. If SOC is less than 90%, then battery will absorb power. And no power will be drawn or supplied to the grid. So whatever maximum power is being extracted from PV, that will be used to supply load as well as charge the battery. But if generation of PV is less than load, then we have to check the storage. If storage is less than 30%, then we move to this side. If it is more than 30%, then battery can supply the load. If it is less than 30%, again we have to, depending upon the SOC, If it is between 30 to 20%, all the loads can be supplied. If it is between 20 to 10, then one non-essential loads are curtailed. And then if it is less than 10%, only essential load are considered.
Is there any way to remember this? It is difficult to see also how to remember this.
So it is, we just have to check directories. There are simple cases. You don't have to remember it. We can, because it is logical. If battery is already charged, you will not charge the battery.
If this flow diagram is given, then we can apply logic. But if the flow diagram is not given, then it is difficult to analyze.
Actually, this flowchart will not be asked. Only thing is some scenarios can be given, like suppose if it can be a part of it can be asked. Suppose a case can be given that there is certain status of the system where SOC of battery is, let's say, 50% and it is peak hour and PV is greater than, generation is already greater than the load. Then what should happen? Such things can be asked. At that time, you have to see all this condition. What should be done in that case? Since generation is already more than the load, so no need to. The load is already satisfied, and since SOC is less than 70%, so it can be used to charge the battery. If instead of 50% it is 70%, then the remaining, the generation minus load, it can be used to feed. This remaining power can be supplied to the grid. So we have to check all the conditions. The main thing, we have to supply the load first. If then additional generation is there, we have to check the SOC of the battery. If generation is less than load, then also we have to check SOC of battery. If battery is sufficient, then it can supply the load. If SOC is less, then we'll have to curtail the load.
When PV is MPPT or off MPPT?
So PV will be at MPPT. It will be at off MPPT in isolated mode. Whenever it is connected to grid, it is in MPP mode only, always.
And sir, in which condition we can say battery will discharge?
So if it is, it will also depend.
No, battery will charge because it can discharge if it is 70, 60, means if we are going less than 30, then only charging
So
SOC.
if suppose if generation is more than load and SOC is less than 70%, we can charge the battery. See here. So here, even in isolated mode, if PV is more than load, here in isolated mode it is 90%. So SOC more than 90%, then battery is not charged. If it is less than 90%, it is charged.
Yes, sir.
So it will charge only when generation is more than load. If generation is less than load, then SOC has to, battery has to discharge. Because generation is not sufficient to meet the load, so battery has to provide that. It will charge only when generation is low.
Yes, sir. And if it is already sir 90%, then it will not charge in any condition.
No, it will not charge because we have to keep that. That is a condition to
Yes.
increase, to keep its life cycle, to maintain its life cycle. So we want to keep SOC within a band. Overcharging, or discharging will result in battery degradation. So entire flowchart will not be asked. You have to make certain conditions you have to remember. It's not, remember, these are logical also. Because if suppose SOC is, battery is already charged, we would not want to charge it. And if generation is more, then only we can charge the storage. If generation is less than more, then battery has to discharge. And depending upon whether if it is less than 30%, so it will, depending upon SOC, it has to curtail the load. So here C in off peak. So this was for peak hour mode. For off peak hour mode, this is C. We have to go to C. C block is this. So in off peak hour mode, if generation is more than load, so whenever generation is more than load, we have to see if SOC is greater than 90%, then battery will not be charged. And the additional generation can be given to the grid. So grid is absorbing here because generation is already more than the load. We have excess generation. If SOC is less than 90%, then battery can charge. And grid is disconnected or it is island. Since it is not, grid is, power is not being supplied to the grid. And if generation is less than load, then we have to check SOC. If SOC is less than 60%, then battery will supply. If SOC is less than 60%, yes, then grid is supplying and battery is absorbing. And if it is more than 60%, then battery will supply. See, these are limits which they have kept. So it varies. This 60 is not all, means we have to take 60 only. It depends on the choice. So that is why these things are these are not hard and fast limits. It depends upon the operator also. So such things will not be directly asked unless it is given that SOC should not go below this level. Battery will never supply. Supply when? So here battery is supplying because SOC is more than 60%. So battery is supplying here.
Sir, if
Yes.
battery is already below 30, then it will never supply na, in any condition.
No, if suppose if generation is less than load, even if SOC is less than 30%, because load we want to maintain, we want to meet the at least essential load we want to meet. So battery has to discharge. See here F in this F block. SOC here is less than 20%. It's between 30 and 20. So it is between 30 and 20, then essential load and non-essential load can be supplied. If it is between 20 and 10, then non-essential load is curtailed. And if it is less than 10%, only essential load is supplied. So less
Yes,
than
sir.
10% only. The battery is also not supplying at less than 10%. PV is taking care because PV is operating at MPP, and only this PV is supplying the essential load when SOC is less than 10%. So SOC is only supplying when it is above 10%. Sorry,
Yes,
battery is
sir.
only supplying when it is above 10%.
Means sir, we are keeping 10 in reserve. After 90, not charging, or below 10, not discharge.
Yes. So this is the minimum limit for SOC 10 and maximum 90%.
Yes, sir.
Because we don't want to over discharge. So this limit is kept to maintain the life cycle of battery. Because if we overcharge or over discharge, then it will lead to battery degradation. So here that
Yes,
limit
yes,
is
sir.
10 and 90%. So is this flowchart clear, or you want me to explain something?
Clear, sir.
Yes, yes.
And this is to give us an idea that how the algorithms are developed, designed. Whenever we want to develop any algorithm, we have to take into account all the possible scenarios, which can cover almost all the possibilities. Just to give all these demonstration are there, have been kept in this course so that we can understand how these things are implemented, to get an idea about all these things. So next one is this design of a smart grid in practical case study. So all these demonstration are based upon the what we discussed in previous week. So in DC microgrid, in isolated DC microgrid, we had two cases. One was a single isolated DC microgrid and interconnection of two DC microgrid. So here also, this is example of a DC microgrid where RTDS is used. Yes. So here RTDS is used. So this 432 nodes. It depends on the size of RTDS. There are several. One rack of RTDS can simulate a system of 72 nodes, and even one three-phase bus is considered as 3 nodes. So you can say only 24 bus system. One rack of RTDS can simulate a system of only 24 bus system. So if you have 6 racks, you can simulate a system of 24 into 6. So it will come out to be 144. That is why you in that example, one case study was shown where one entire Indian grid. So entire Indian grid. This is case study for that only. Entire Indian grid, because it has more than 6,000 buses, more than 500 generators. Such a huge system we cannot simulate, at least in this RTDS, because the RTDS which is available in at IIT Roorkee, it has 6 racks. It has 6 racks. So these are 2 racks in vertical and then 3. Just like the system which is shown. So IIT Roorkee has this RTDS like this. So 6 racks are arranged like this: 1, 2, 3, 4, 5, and 6. And each of them can simulate a system of 24 bus system. At a time, we can use all the 6. So one person can, if someone is already using a rack, we cannot use it. When all are empty, no one is using any rack, then 144 bus system can be simulated in RTDS. 6 racks of RTDS. So this Indian grid, which has more than 6,000 buses, this transmission network was reduced. So we get a reduced transmission line model. So we can use reduction. There are certain reduction algorithms so these algorithms, they combine certain nodes into single node. So they will aggregate all the generators and load at that single node. So all the let's say in some districts will be clubbed together as one node. It all depends upon the topology of the network. So the topology of network is used. It is taken into account while doing this reduction of network. So after the reduction, 120 buses were there. So the entire network was reduced to a 120 bus and number of lines. I think I don't remember exactly. So around 210, I think. So 120 buses were there. So now 120 buses we can easily simulate in this RTDs. So 120 bus system was modeled in RT. You can say RSCAD. RSCAD. So RTDS is the hardware. These racks are called RTDS, real time digital simulator. And this RTDS also has a software platform which is called as RSCAD, real time simulation computer aided design, RSCAD. Yes, sir, we have PSCAD, this one software. MATLAB is also there. And there are other softwares also. So in RSCAD we can create this entire network. There are several blocks available. Whatever we want to write, there are models for transmission line, generators, transformers, loads, everything. Even storage and electric vehicle also. So all these we can model inside the RTDS and RSCAD and simulate it on RTDS. Then since this model is available in RSCAD, at any bus we can integrate a microgrid, a DC microgrid, which is a hardware setup, which is built in the lab. So these are the components of uh, that DC microgrid. One is this PV. So we need a PV source, PV generator, then wind generator, wind which is wind emulator is used here for creating that wind source. Then one rooftop PV, diesel generator is there, storage, loads and converters. So this is using semichron IGBT converter. So all these are real hardwares. This PV emulator, it can take into account all the weather conditions, even shading effect and static and dynamic amplitude testing. So do you know what is shading effect? Have you heard of shading effect? So whenever we have these several solar panels, either on the rooftop or even in the open area, open field. So yes, because it can be called clouds also. So generally it is generally whenever we want to install these solar panels or we want to build a solar farm or even for rooftop solar PV, first of all a detailed study is carried out. Where should we install that solar panel or solar farm? Because there should not be any shadow effect. So if shadow is there, the sunlight, the input to the PV panel will reduce. So after considering that, considering in open field there is no shadow as such. So there the shading effect comes into picture when there are clouds. So in that case, cloud may not always be covering the entire solar farm area. Sometimes the cloud may cover few panels or a portion of the entire farm. So in that case, what will happen? The output of that portion will reduce, and that sometimes has other type of effects also, adverse effect, to reduce that shading effect. And even within that shading effect, while there is some shadowing effect, we want to maximize the output from solar panel. So for that, these dynamic MPPT algorithms are used. So to take into account the shading effects, while design of PV panel also, the construction, the manufacturer also has, they also keep into mind the shading effect, and they will give some protection for that within the panel. And the inverter manufacturer, they will have to develop such algorithms which can extract maximum power from solar even during shading cloud covers. Then storage are two types. One is lead acid and ultra capacitors also. We have seen in previous weeks, one was we have studied this hardware in loop. So there are two types of hardware in loop. One that we studied was controller hardware in loop, control hardware in loop. And second one is power hardware in loop. So in this case, control hardware, there is exchange of signals. Here there is exchange of power between the device under test and the real-time simulator. So this hardware in loop can be open loop as well as closed loop. So if it is open loop, then there is only unidirectional flow of power or signals. Suppose this is RTDS, and we have modeled a network inside RSCAD. Then at certain bus, I want to take output from certain bus. Let's say I am taking voltage and current, and then I have a power amplifier here, and in between we also have this digital to analog converters. Then here we will be having analog to digital converter. This is not required. Directly analog you can feed to the test system. So here we have the test. So let's say this is a relay. So we are taking voltage and current signal from one of the buses from the network which is built inside the RS card. Then we are taking the output, feeding it to the power amplifier. This power, because these current and voltage are within plus minus 5 volt and 5 ampere, because that is the limit of the output which we can take from the RTDS. But this relay, it works at, if it is single phase voltage 240 volts and some current also. So we will have to increase this voltage from 5 to 240 volts. So this will be done by the power amplifier. Then we can operate this. So inside this relay, again we will be having those analog to digital converter, signal conditioning block, the anti-aliasing filters, and then DFT block, which will do the phasor estimation. And based upon that, it will give one trip signal. So we can test this relay. Suppose if we want to install a relay in the existing transmission system, or let's say distribution system only, then we can model distribution system here, take output from particular bus where we want to install that relay, and then pass it to power amplifier and then give the output to that relay which we want to test. And then we can observe whether it is functioning as per the desired requirement. So this is example of open loop system. When will it become closed loop? Can you tell? How can we make it closed loop?
We have to take feedback, sir.
Yes. So what we can do, the trip signal which we are getting, which we are seeing on oscilloscope, we can feed that trip signal again via a ADC block to this RTDS. And within this network also we have kept relays, which is that virtual relay which is there in the system. This is physical relay, but in system also we have relays. So what we can do, we can use this signal to trip that relay. So the system inside that also that relay will be working. So this is a this is a closed loop system. So this is one example. We can do other type of feedback analysis also. So this is control hardware loop. So here we can see, and first, so open loop and closed loop. Then it is why do we use this hardware in loop test? Because it is cost effective and safe to test physical devices. Yes, so it is cost effective and safe to test physical devices, and hardware devices are interfaced to the real time simulator. So control hardware in loop, we have discussed the physical controller protection. Relay devices are interfaced with the real time simulator and exchange analog and digital signals. So if they exchange, if there is a bidirectional flow of signals, then it is closed loop. If it is unidirectional, then it is open loop. So here the exchange on signal is at low voltage levels, 5 or 10 volts. Even if this is 5 volt, so it can be 5 or 10 volts. In some simulators can also give an output of 10 volts also. Then second is power hardware in loop. So here the test devices are power devices which draw huge amount of power, such as motors, inverters, generators, and transformers. So these are interfaced with the real-time simulator. So here we have, instead of this relay, we will be having these motors or high power devices. The same thing we can do open loop as well as closed loop here also. So instead of this test system, we can connect entire DC microgrid also, as shown in one of the case studies. So one DC microgrid was connected to that Indian grid. So that first of all, that Indian grid, huge grid, was converted into a reduced Indian grid. Then at one of the buses, this here power amplifier, and then this Just a minute. There is some problem. My monitor is not working. It has changed. Switch to this. So can you hear me?
Yes, sir, audible.
Even slides are also visible.
Yes, sir.
I am not able to see that screen. I don't know. But I am able to write also.
There is three red line. Yes, sir, it is changing.
I am able to do everything, but I am not able to see it on my monitor. Okay, let me write. Okay, so we are talking about this hardware in loops. So there are two control and power hardware in loop. So in control we have these devices which are low voltage, which require low voltage signals, and power hardware in loop will require high power signals. So they will exchange these power signals between the real-time simulator and the hardware. So this is the diagram for those two CHIL and PHIL control hardware in loop and power hardware. So in both the side we have this real-time simulation. This is the real-time simulator, or we can say RTDS, and here also we have real-time simulator. Then after the real-time simulator, it is digital to analog converter. The output from even some of the RTD, they also have analog outputs also. So you can directly get analog outputs also. If the digital outputs are taken out, then you have to convert them into analog. Then the next step is amplifier. Then output of amplifier goes to the device, so it will give the analog output. Then from the device we can get feedback. Since it is a closed loop, then that will go to digital to analog converter of this simulator, and then inside the network. So this is CHIL. So these two things you should remember. These are very important. So what is the main difference between PHIL and CHIL? In PHIL we will require these additional voltage and current sensors also. Because the output of this powered device under test, it is we will give high voltage and current signals, which we have to measure if you want to feed it into the system, into the real-time simulator. And we have to measure them. Because in CHIL, the device and the test will give signals which are at low voltage. But here, power device, they will give high voltage and currents. For that, they will need explicit voltage and current sensors. So we can use them, and then the next step will be analog to digital converter and then filters. Is this clear?
Yes, sir.
Next is this AC-DC distribution network. What is the difference between transmission network and distribution network? So this we have discussed earlier also. Do you remember? What is the difference?
RBX is more
Yes.
is less in distribution network, is more in the distribution network, less than the transmission network.
Yes, correct. So R by X ratio is quite high in distribution system, and because of that, we are not able to use the overflow algorithms that we use for transmission system. For transmission system, we use this Gauss-Seidel. Gauss-Seidel is not used, but it is the most basic one. Then Newton-Raphson is most widely used. Then we have fast decoupled load flow. So this decoupling is there because of low X by R ratio. Low R by X ratio. X is high in transmission system. So because of high X by R ratio, we are able to get this decoupling between. So power is, what is the decoupling in transmission system? How is power related to, power is directly proportional to voltage or theta?
Square of voltage.
No. In transmission system, it is dependent on theta. So you say the P is E1 into or V1 into by X sine delta, and Q is, or you can say P will decide frequency and Q will be decided by this voltage difference given with. So this is a decoupling that we get. P is directly related to frequency and or theta, and Q is directly related to the voltage. So this decoupling is possible because of high X by R ratio in transmission system. So these are the different power flow algorithms that we are able to use for transmission system, but we are not able to use them for the distribution system because of high R by X ratio. Also in distribution system, especially now, earlier the distribution system was almost radial. They are connected in meshes are there in between to increase the reliability, but those are used only when there is some problem, some contingency or some fault. But usually the distribution system used to operate or still operates in radial fashion only. And in distribution system earlier there were no converters, nothing, only simple loads were there. induction motors were there. But now and in future, because of smart grid, because of interconnection of so many different types of distributed energy resources, and even DC microgrid or AC/DC hybrid microgrid at particular buses, the methods which we were using for power flow calculation or power flow studies of distribution system are also they also need to be changed. Because for distribution system, one of the most basic method is this forward and backward sweep method for the power flow studies. But that is applicable only for radial distribution networks, not for mesh, and not for such AC/DC microgrids also. Because these are inside, we can see here we have radial. Initially radial, then we have rings. We have several rings here. So for this we need different types of methods which can support these meshes, and also modeling of so many components is required. In distribution system, transmission system is how only in India more than around 6 to 7,000 buses are there. But in distribution system, there are lakhs of buses. There are so many loads, lakhs of loads for even for one discom distribution company. So the magnitude of the system, the distribution system becomes very large. And the number of components is also too much. We have to model each and everything. So we'll have to model converters, different types of transformer connections, unbalance also when we do transmission system, and when we do the steady state analysis or load flow studies for transmission system, we consider that the transmission system is balanced. So that simplifies our analysis. But here we cannot assume that, because distribution system is inherently unbalanced. It is always unbalanced, even without fault. The normal operation is unbalanced. So that also we need to take into account while doing analysis. We cannot do per phase analysis here. For each phase we have to do different analysis. So each phase has different current. There is unbalance. We have to model all these new types of DERs, solar, wind, micro turbine, storage, different types of converters. So that is why the distribution system analysis is very challenging. It becomes very challenging. And if we integrate these AC microgrids also on a particular bus, then it will become further challenging. So here we'll see what type of buses are there. In transmission system, there are three types of buses. What are these? Can you tell?
Lag bus, PV bus, PQ bus,
Yes. So one is slack bus,
PV,
PV. Yes, one is PV bus, and another is
PQ bus,
yes.
PQ bus.
So load bus is PV or PQ?
It's PQ bus.
Yes, load bus is PQ because for load P and Q requirement are specified. If we write equation, suppose there is a system with n buses, and we want to write equation for each bus, then we can write equation for each bus for P and Q in terms of V I theta. We can write. So in terms of V and theta, we can write. So at each bus we will have two equations, but there are four unknowns: voltage and angle at each bus is unknown. Then P and Q are also unknown. and we have four n variables and two n equations. So we cannot solve such a system. So for that, to solve such a system, we specify. So out of four n variables, we will specify half of them. So at each bus, out of four, we specify two variables. So in slack bus, what are the two variables which are specified and what needs to be calculated? So there are four variables: P, Q, V, and delta. So at slack bus, we assume that
V and
yes,
theta
voltage
flow.
magnitude as well as angle is available, which is 1 angle 0. We consider it as reference bus. Then at load bus, P and Q are available, so we have to find voltage, angle as well as magnitude. And at PV buses, P and V are specified because at PV buses, generation buses, they have two controls. They have governor control as well as automatic voltage. AVR also is there. So they are able to regulate their voltage as well as the input P and V. So P and V are, we can assume that they are specified. And so we have to calculate Q and delta at PV buses. So these three types of buses are there for the AC system. For DC system, we have two buses. Why only two buses in DC system?
DC no reactance and angle.
Yeah, because there is no
Q and no what angle.
no frequency. So no reactive power and frequency is there. So only P and V are there. That is why there are only two buses. One is load bus, which will be P, and then another is voltage control bus, V buses. Next is this. So AC/DC load flow. This we have also. We have discussed this. Load flow solution for transmission cannot be used because of in transmission system there is low R by X, but here we have high R by X. And for DC, for distribution system it becomes more complex because of the number of components is huge. So it becomes more complex because of number of components, high number of components, high connections, then unbalance in the system is also needs to be taken into account. All this also the load model. Generally, when we do power flow studies for transmission system, what type of load we consider? What is the assumption for load type? So what type of a bus is load bus? It's a
PQ.
PQ bus, right?
Thank you.
So it is assumed that the loads are constant power type for transmission system. But in distribution system, we cannot assume this. Because in transmission system, we aggregate the entire load of entire state, let's say. One bus is, if let's say one city is there. So aggregate P demand is almost constant on a daily basis. Or at least for few slots it doesn't change much. So it is on an aggregation basis, this assumption is it, it can be taken. Such assumption is valid. But when we are working in for distribution system, and each load type we have to consider. There can be different types. There can be constant power, constant impedance, constant current load, or even mixed zip model. So there can be proportion of constant impedance, constant power, and constant current. That is why it is called zip. Impedance, current, and power. So each of them will be having a particular weight, and some of those weights will be 1, depending upon which of these is given more weight. And then there are exponential models, load models also. So different types of models are there based upon the different equipments that we use at our homes. Refrigerators, air conditioners, all these detailed studies have been conducted to find out the type of model for each of these equipments. Then we have to model storage and DC loads also. Transmission system, we consider loads are AC, but here we have to model DC loads also. Then we have to take into account prerequisite of control objectives by the converters, and also representing the operating state of combined AC-DC system. So overall, it becomes very challenging. It will become more challenging if there are more number of AC-DC microgrids. One may say that AC-DC load flow or power flow is also done for transmission system also. Yes, because we have HVDC systems also. But HVDC systems are very few. Overall, the system is AC. But when the distribution system will become more smart and more number of microgrids are added, the DC component will become significant. So these are the different converter models. 3 converter models are there. One is DC-DC. So this DC-DC converter can be either this buck boost or buck boost, and that will determine the relationship between this voltage on both the sides, as well as current. It is similar to transformer, but it is DC equivalent of the transformer. So step up and it's boost and step down. But these non-isolated type of converters, DC-DC converter, they have only a ratio. They can provide a transformation ratio of only 1:4 or 4:1, depending on the boost or buck. Beyond that, we have to use non-isolated type of DC-DC converters. Then we have this AC-DC voltage source converter and LCC, line commutated converters. So these 3 models also we have to write their governing equations while carrying out the power flow studies. Then the available distributed energy resources can be divided into 4 types. So these are the 4 types. Type 1 delivers active power, such as power, solar PV and fuel cell. They only deliver active power. And type 2 are they deliver P and Q. So just as the conventional synchronous machines, cogeneration, gas turbines. In type 3 is they deliver only Q. So synchronous condensers or compensators, the reactive power compensators, they come into this category. So if they deliver only Q, what will be power factor?
Negative.
No. So power factor will, how do we define power factor? Power factor is ratio of P and S, right? Active power by apparent power. So here it is delivering only Q. P is 0. So power factor will become 0 because no active power is being supplied or absorbed, consumed or delivered. Only reactive power is delivered. So power factor becomes 0. And type 4 is similar to our induction generators. It delivers P active power and consumes Q. Why does it consume reactive power?
Maybe line is the leading power factor.
So, can you repeat?
Maybe because of the line, maybe it's the leading power factor, so it has to consume Q.
No, it will be having a lagging power factor.
Which means it's a leading power factor, so that it has to consume Q. It's not generating Q, sir. It's absorbing Q.
Yeah,
Then
it is consuming Q. Yes.
correct.
It is
So
consuming Q with
consuming Q means already Q is more, so that it has to consume.
no. Why does it? Can it not operate without consuming any Q? Reactive
The
power.
leading power factor is also a problem, sir. It also draws more current.
Winding of induction generators will consume Q, na?
Yeah. Yes, that is correct. Not just winding. The principle which governs the induction machine, it requires reactive power. So that electromagnetic conversion or electromechanical conversion, that requires reactive power. So where is that reactive power goes? Where does it go? Because P active power is delivered, or it is, suppose if it is an induction machine or motor, then it will consume active power. So whatever mechanical motion happens, it because it will deliver some work, it will do some work because of that active power. But where does that reactive power goes? So it goes in establishing that magnetic flux, so which generate that work. The storage of energy, the conversion between electrical and magnetic energy, that conversion is possible because of that reactive power, the reactive power component. And the actual work which is done, it is because of the active power. So if the conversion process takes more reactive power, then conversion process is not a good one. So we want Q to be less and we want more active power output. So that reduction of power factor causes several problems because our system are designed for certain level. Like thermal rating lines, transmission lines have their ratings. They have thermal limits. They have current limits. Suppose, but for in distribution system, if there are several induction motors, and they start drawing very low lagging power factor, it becomes a very low PF load, then the reactive power requirement will be huge, and that will increase because the overall current drawn from the transmission line. So that will create additional losses, heating of transmission lines, and even distribution lines. So we don't want the power factor to be low. We want it to be close to 1 per unit. It's a 1 UPF power factor we want. So that is why for industrial and commercial consumers, there is a power factor penalty. They have, if their power factor is too low, then they are penalized. So what do they use to improve their power factor?
Generally, capacitor.
Yes, they
Capacitor
will
bank,
use shunt capacitors.
capacitor banks,
Yes.
and then we can install these synchronous machines also.
Yes. Yes, we can use that. Overexcited synchronous machine can provide reactive power. It can supply reactive power, so it will supply the reactive power required by that induction machine or any load which is drawing the factor. Correct.
Small doubt, sir.
Yes.
Sir, in case of this induction generator, it will give active power and consume reactive power. Then we have to use capacitance also starting with induction generator.
Yes, we can use.
Okay, sir. At the case with induction motor, we use shunt capacitors.
Yes,
Like that, we have to use induction generator also,
yes, we can
some
use.
capacitors. So
Yes.
that only we can manage the unity power factor.
Yes, that is
Sir,
correct.
another doubt. Sir, another doubt, sir. Actually, the power factor is maintained usually to reduce line losses, but at the place of generation only, we are getting low power factor. Then what is the wrong with not having capacity?
So that is why we are not using induction generators. We are using synchronous generators.
Sir, but the case with the
Hmm.
wind farms are using the induction generator.
Yes,
Then
they
they will use
use DFIG.
there is no need of using capacitors, sir, to reduce to make the power factor unity.
That for converters, because this DFIGs, all these, they have a converter with them. So they are interfaced to the grid with the help of these converters. So converters, we can manipulate the firing pulses in such a way that they can operate close to unity. That we can do. We can ensure the control in such a way. Even HVDC, whatever the HVDC converter transmission lines that we use, they also have these reactive power compensators. They also have to use that. Even the converters also have such compensators if required. So
Okay.
big
So is there
converters,
any
they have compensators.
necessity of compensating that reactive power, sir? Because it's at generating end only reactive power is generated, then it is not transmitted to loading. Then is there any necessity of compensating that reactive power at generating DFI, sir?
So I could not hear. Can you repeat once again?
Sir, because at the generating end only it is reactive, that reactive power is consumed. Then is there any necessity of compensating that reactive which is not transmitted through transmission line? Then what is the necessity of compensating that reactive power at generating end?
No, no. HVDC or whatever this, if generator is taking reactive power from the transmission line, that is why we want to compensate so that we do not need not draw the reactive power from the transmission line. We can locally supply that reactive power. That is why we use compensator. Because if we overdraw reactive power, then it will affect the voltage profile. The voltage will reduce at that point, at that bus. So we locally supply that reactive power so that the requirement from the transmission system reduces.
Okay, sir. Okay.
The same thing we are doing at residential. These industrial consumers are also doing the same thing. Because they are consuming more reactive power, their power factor is reducing and voltage is also reducing sometimes at that bus. So locally we supply that reactive power. So voltage is also maintained and power factor improves. Because voltage reduces because large amount of current is drawn. So losses increases, so the voltage also reduces. So all these things we can avoid by using compensation. The next is this grid connected DC microgrid. Here there are two types of transformation we have. discussed, right? One was, do you remember what are the two types of transformation from ABC frame to two different frames?
I and Q and alpha and beta, I think.
No, not I. It is D.
P and Q.
No, no, D. DQ.
Oh, sorry, DQ.
Yes. So one is DQ and second is alpha beta. So here alpha beta has been used, and because alpha beta is used, the controller which is used here is not PI. So now I have a question for you. In this figure, two types of controllers are used. One is PI and another is PR. So why have we used PI? Why can't can we replace PI with PR? That is my question.
No.
Why? We have discussed this. Let's try to recall. Just think little bit. Why can't we use it? Replace PI with PR.
PR use alpha beta and PI use DQ.
Yes, but so what is the difference between this DQ and alpha beta quantities? But here for DC bus voltage control, we are not using any DQ frame. Here. So if you see the input for PI controller in DC voltage control, you can get the idea why we are. What is the requirement for PI? Can we use PI with AC signals, AC input, sinusoidal quantities?
Because sinusoidal is changing, so we cannot use. We are using DC controls.
Yes, we prefer. It is preferred. PI is only used for DC inputs. That is why in DC bus voltage control, PI controller is used. It works well with DC inputs, but for sinusoidal inputs, PI cannot be used in its original form. So that modified version of PI is PR, proportional resonant converter. We can see the equation of PI and PR below. This is PI and this is PR. So here we have only Ki by S. So there is one pole at S is equals to 0. This. But here this is the difference between the two. For PR we can provide sinusoidal inputs and alpha beta are sinusoids. DQ are DC quantities. Alpha beta are sinusoids. That is why we are using PR here. We cannot use PI here. Okay, this is clear.
Yes.
Now there are more questions. First question is the modes of power flow control strategies is R. Which one is correct? Yes or are correct.
C and D.
Yes, isolated and grid connected. This was easy. Now, in this was a question. Such type of questions can be asked, which I was telling based upon on that flow chart. In isolated mode of power flow control strategy, if PV is so generation from solar is more than load and battery SOC is more than 90%, then which of these operation is correct?
Option D, sir, of MPPT.
We discussed whenever it is isolated of MPPT.
Not always of MPPT, but in this case, because battery is charged, if battery is less than SOC is 90, less than 90%, then it will still uh, operate at MPPT, right?
Yes, yes.
Because generation is more than load, and if SOC is less than 90%, then we can extract maximum power and charge the battery. It will be good for the storage that we extract maximum power from the PV. PV operates at MPPT, loads are met using conventional grid. Battery supplies load and PV operates at of MPPT. So PV operates at of MPPT. And what will happen if instead of isolated mode, it is in grid connected mode?
It will operate at MPPT, sir.
And why?
Because grid is there, it will charge the grid, give the
So
grid.
yes, we'll not say charge the grid because yes,
Yes,
it will supply to the grid.
sir. Yes, sir.
Especially if it is peak load, then it will be beneficial for grid also. Can supply the peak load requirement. Is correct. Okay, so we discussed all these things. The peak hour. So here, this is a kind of a summary. So this you can remember for all the three cases. This will be helpful if you get any kind of question for this power for control strategy of DC microgrid. So in peak hour, the priority is either to supply the grid or draw the minimum power required for essential loads in grid interactive DC microgrid by ensuring that DC bus voltage is within the limit. So every time our main goal is to reduce the power requirement from the main grid. We can supply it. If nothing is possible, if storage is also discharged, if generation is also less than load, then nothing can be done. At that time, we have to take power from the grid, but only will take power for which type of loads. So, if storage is discharged, generation is less than load, then what are we going to do in grid connected mode?
Only critical supplies we will give.
Only essential load, sir.
Yes, essential load. And if that generation is less than even essential loads, then we have to take power from the grid also. In that case, only we'll take power from the grid. Okay. Then off peak hours. In off peak hour, the conventional grid is able to deliver enough power at low cost. So at that time, what we can do? Why are we not charging the storage at peak hour? Can you tell? Yes. I said in the class scenario that storage is discharged, generation is less than load. Then we are supplying the load, essential load. Why can't we draw power from the grid and charge the storage at that time? Can we not do that?
More load will be there on the grid, sir.
Yes. First is that we don't want to overburden the grid. Second, it is also costly at peak hour because the demand is much more than generation. So if the prices the day ahead or real time market prices are also quite high. So if you go through these websites of IEX or PXIL, HPX, you can see the prices for day ahead market as well as real time market. So you can see during peak hours the real time market prices are quite high in comparison to the off peak hours. So
Moreover,
yes,
moreover, transmission line will be also loaded at that time, and you are flowing power reverse also.
reverse, reverse.
Reverse means that charging of batteries.
So it's how
So
is it reverse then?
reverse in the sense, then what you say, what I want to say, it is opposite to the load. So then line will be more loaded.
It is. I could not understand that opposite to load. How opposite to load? Because now battery is also acting as a load now while charging.
Once
The,
we say
the,
load is means that commercial load. Battery is we are taking as a storage. It is though it is a load, but it is a storage. That is my way of looking at it.
yes, storage is charged during peak hours, and yes, it will congest the transmission.
That is
That
what that line capacity will also be congested at that.
yes, that is true. The transmission system will be further congested. That we do. So in any way, this is not at all desirable. Economically also, technically also, both ways this is not advisable. The storage would always want to charge at a low price and discharge at a higher price so that it can earn the price arbitrage. So that is one profit for storage. That is how the storage is going to recover its cost. One of the ways. It can also provide several other types of services. What are the other type of services that storage can provide to recover its cost? Can you name some services? Yes. That is ancillary services is one good example. So now even in the recent draft ancillary services regulation, these are also correct. So even we have in Indian grid also, Indian power market,
Sir, CG from common grid.
conventional
CG
grid, yes.
conventional grid, yes. Sir, in case it is connected to grid and if he is not supplying means it is supplying less than load,
Okay.
then it can take from the batteries. Batteries are charged or
Yes.
from the grid
When it is connected.
when it is connected.
If battery SOC is good enough, battery can
Take from
discharge.
battery.
Yes.
No need to go to the grid.
No.
But
So
sir,
if
if
it
it
is off peak hour,
yes sir, if it is off peak hour,
yes, and battery has sufficient charge, then battery can provide. Otherwise, battery can charge.
sir, if
Because
it is off peak hour, if we can take from the grid, then peak is not already there, then it will not be costly.
yes,
And if we not take from battery, battery life cycle will also increase.
yes. So we have to maintain a state of charge of battery so that we can discharge during the peak hours also. Or when
Yes,
the
yes
we
sir.
have to keep battery also. We have to keep at that.
So at that time, taking from grid will be beneficial.
Yes, we can do. Depending, it will depend upon the SOC of the battery.
Batteries are sir full charge, SOC
Then,
greater than 90.
then,
Then,
so then we can discharge the battery also
acha,
to certain level. Then
yes sir, yes sir. Means I want to tell that sir, if we are using battery less, then its life will be more.
yes, that is correct.
Yes sir.
So whatever flowchart that we have seen, it is a rule-based strategy.
Yes sir.
But if we do the same thing using a kind of if we formulate an optimization problem for that, and we want to minimize the overall operational cost, then it may happen that the discharging cost of battery is higher than the off-peak hour energy drawn from the grid. So then the optimization problem would try to take power from the grid.
Yes sir.
So because it's a rule-based strategy, so we are following certain rules based upon SOC levels. But yes, if we do some optimization, then things can change. So there are only two options: either discharge the battery or take from the grid. So whichever is more economical, that will be done. That is correct.
Yes sir.
Good point. So in off-peak hour, conventional grid is able to deliver enough power at a low cost, so we can charge the battery. Charging of energy storage is preferred along with supplying loads. So we are that this is what you were saying. So can charge the battery as well as supply loads, so that stored power can be utilized locally when the peak demand occurs. The storage is also being charged and load can also be supplied because it is cheap power is available from the grid. And conventional grid should not be driven into peak demand. So we have to ensure this also. The demand should not be that much during off peak hour that we create a new peak. That also we have to keep into. So the controller has to take care of this fact also. That it should not happen that the power is cheaply available, so we draw a lot of power and then create another peak. That will again congest the lines. So it happens. It happened once in I think in Uttar Pradesh, the Discom they started one new scheme, an incentive scheme for the consumers during off-peak hours. If they charge or they operate their residential equipments during off-peak hours, they will be given certain benefits in their electricity bill. So the same thing happened there. So several people they shifted their loads from evening to night, and it created another peak. So this kind of problem can happen. So this also we have to consider. We should avoid a second peak.
Yes sir. Population of UP is also sir more load. If shifted on,
And also whenever we are getting something cheap at a cheaper
yes sir.
price, and we all of us would want to
That strategy sir nowadays applying Flipkart Big Billion.
yes, everyone tries to uh, reduce the cost. Then last one is isolated. So in isolated, when conventional grid encounters any failure or outages, it will be microgrid will be isolated. So microgrid is operated under extreme scenarios. So if in first case if generation is less than load and SOC is also critically low, then there will be load shedding, right? Because load is more and battery is also not that much charged. So we can only supply the essential load. So these are some. So this is a summary of that flow chart. You can remember this to answer most of the questions. And second is if generation is more than load, and this is another extreme. Here generation is much more than load, and SOC is also more than 90%. Then PV has to operate at off MPPT. So these are the two extremes. Correct?
Yes, sir.
So this is the same a summary of that only. Shall we move ahead or will we discuss this? This is the same thing which we have discussed. All the three modes and the status of battery depending upon the SOC. If it is more than 70%, it will be idle. It will not charge or discharge. Less than 10% also, it will not discharge. If it is less than 70%, it will absorb. Well, all these cases have been covered here. Right? So the next question is, this is also easy question. Two type of hardware in loop simulations are. Which is the correct
CHIL, VHIL.
answer? So
E and D.
what is CHIL? Full form of CHIL?
Control, sir. Control hardware in loop.
Yes. And PHIL is power.
Power.
This also, please remember this. It's important. So these the
Yes,
next
sir. There
is
was a question in assignment, sir.
then DC microgrid functionalities. Which one of these is or are?
All of them.
Stability margin, flexibility, and grid support services. Correct.
Yes, sir. All.
Let's see. So these are all the different DC microgrid functionalities. Starting with grid support. So grid support services means it can provide these ancillary services. Voltage support, frequency support, black start services, all these things it can provide. So in 2022 December, there was blackout in Mumbai. One generator was not available. It was taken out due to maintenance. It was to be again synchronized, was about to be brought on bar after a few slots, and that happened within after a few hours, and that blackout happened before that. So several studies were done here at IIT Bombay also. So it was found that if at that time such energy storage or such microgrid funds would have been there, then that could have been avoided. So we can provide like certain case of when are we going to when do we require black start services?
What was the question?
When do we require black start services?
Grid failure.
Yes, blackout, brownouts. We require all these black start. Then second is scalability. So seamlessly it is possible to seamlessly add or remove power units. We can add more generators, more DERs. And DC microgrid can also ensure stability, sufficient stability margin in steady state and transient operation modes. Last is flexibility. So there is a possibility of reconfiguring the system online during faults by disconnecting from the utility grid. So during faults, this microgrid can operate in isolation and still supply the load. And also can help in the reconfiguration of the system so that the power flows will be redirected and the load can still be supplied. So this diagram is a very good diagram. So many things. One diagram covers several things. Starting from the innermost circle, grid tied inverter. After that, it is the operation mode session. In grid tied, it can offer so many services. And also for normal and abnormal condition, also there are two colors are used, blue and red color. So in grid connected mode, so many services can be provided by the PC microgrid. Grid support services. So in grid support services, we have active power regulation, reactive power regulation, harmonic attenuation, so resonance damping, grid harmonic filtering, local harmonic compensation. And in abnormal, it can provide resiliency to voltage side. Low voltage right through, resiliency to impedance variation, overcurrent protection, over voltage protection. In transition mode also it is synchronized. This GI, it's a transition, grid to isolation. Abnormal to grid or isolated. The autonomous to grid or islanded. The synchronization. There is one figure, next one. Next is yes. A typical DC microwave, which of the following is not a mode of operation?
Autonomous.
It's
Autonomous.
D.
None of the above. Autonomous is also
None of the
there.
above.
None of the above is correct. So we'll see that autonomous. I was talking about the- where is that figure? Next.
B is the answer.
Yeah, this is the figure.
B.
Select correct option for control layers in DC microwave.
B.
B, yes, B is correct. So zero primary and secondary and tertiary. So this is that figure. So here we can see this is a hybrid AC-DC microgrid. In this, within this, we have a DC microgrid also. If you see, there are two switches, and this the status of these switches will decide whether the microgrid is operating in which of the three modes: islanded, grid connected, or autonomous. So, what will how if it is grid connected, then both switch S1 and S2 are closed, right? This is here we have switch S1. This is S1 near L. Then S2 is connected to after PCC. S2 is after PCC. So islanded and autonomous are decided based upon the status of these two switches. If SW1 is closed and SW2 is open, then it is islanded because it can still supply the PCC loads. If SW2 switch is closed and SW1 is open, or SW2 can be open or closed also. But if SW1 is open, then it becomes autonomous. It cannot supply PCC load. So the difference between islanded and autonomous is that whether it can supply PCC loads or
What is the example? What is the example of PCC load?
not. So here any load can be connected. It depends upon the structure of the network. It is not always.
No, but it is AC or DC?
This side is AC because it is directly connected to AC bus.
That means PCC load is AC load.
Yes, this is AC. PCC load is AC. Yes, someone was raising hand. You want to ask something?
Sir, as it is DC microgrid, then secondary control layer, why we end up controlling this? So why frequency is coming into this?
See, because it's a hybrid AC-DC microgrid. That is it. So DC microgrid is a part of it. Overall, if we see, if we consider this entire microgrid, then it's a hybrid AC-DC microgrid. So we'll require V and F controls. But if we talk only about DC microgrid, then only we have to think about that voltage, VDC, bus voltage evolution. So there are four control layers. One is zero level, which is very fast. So as we move from zero to tertiary level, the time required for those control increases. So highest is more than 10 seconds. It's a slow process, which is power flow control or optimization problems. Then secondary level is microgrid synchronization or and this BF control. Primary is automatic load sharing and grid support. Zero level is for inverter variables. Control of grid tied inverters variables. Zero level is fastest, then primary, then secondary, and tertiary. So it will always happen like that. Relay also, protection system also. We have backups, right? So backup should operate first or the primary protection. Which one?
Primary, sir.
Yes. Similarly, here also we have. So here we can say zero level is the most primary control. Then we move up at above level, upper, higher level. So the lowest level is the zero level, which is the most primary control, which is quickest. Then if it is not able to meet that requirement, not able to control that disturbance, then primary will take care. If primary is also not able to fully um, control that disturbance, then secondary will come into action. And then even if secondary is not able to bring back the system to normal, then tertiary will operate. So this is a hierarchy to this one also. Next question is, which of the following is are correct about DC microgrid? First is consists of only DC bus, and DC bus is for interfacing DC sources and DC loads. Then operates in three modes and serves critical loads during grid outages.
B, C, and D.
It consists of A, C, and D.
B, C, D.
B, C, and D.
Why not A?
Only DC bus, sir. It can supply also AC.
No. Well, DC microgrid will have AC.
Oh,
Have AC bus.
it can supply AC loads with help of
It can
converter.
supply AC, load, but bus will be
Only this.
DC.
Yes.
It can supply AC load with the only thing that converter will be required. DC to AC converter. What will be correct answer?
Then all will be.
Even I have put this BCD.
In fact, all are correct. All are correct. You have to.
All are in this case. Means if we So all are correct. Next is type 1 DG. Which one is type 1 DG?
C is the answer.
Uh, yeah, deliver speed. So example of type 1 DG is, what's the example? What type?
Batteries and PV panels.
Yeah, PV panel, fuel cell.
Sir, DG full from
Where? DG, distributed generator.
sir,
Or we call them DER also.
not
Distributed
diesel
energy.
generators.
No, not diesel generator here. DGs are generally wherever you will find DG or DERs. Distributed generation or distributed energy resources. These are the
Yes, sir.
widely used uh, short forms for that. I think this is last question. Oh, there is a select the correct statement about AC/DC power flow. First, Newton-Raphson is the best method. Second, there are 4 types of AC buses and 3 types of AC buses. And converter modeling is not an essential requirement or none of the above.
None of the above.
Yes.
D.
Which one?
Sorry. No. There are 3 types of AC buses.
Yes, 3 types AC buses and 2 types of DC buses.
Two types of AC.
So D is the answer. None of.
Yes, Newton-Raphson is also not the best method. You have to use another method. Distribution system. Specific methods we have to use. And converter modeling is also an essential requirement. So D is good. Yeah, so questions are all clear. Do you have any doubt?
We discussed last time. You will revise so that we will all pass the exam.
Yes. Yesterday we received one mail
Sir
from.
told that it is 21.
If you will not revise, then I will fail in exam then.
Actually, yesterday we had received one mail, so I think they are also PMRF team. Sorry, NPTEL team is also willing to give us organize one official session for this.
Because a lot of things we have learned, so revision and then paper is also required to be clear. Na?
Yes, that is important.
So
So
Sir, today is the last official session, sir.
no, tomorrow, one more week is there. Na? Week 12 is also there. 1 week is left. So next session
Yes.
will be on next Tuesday, 17th.
Yes, sir. Yes.
So I had given preference of Saturday 6 to 8 p.m. So even if that official session is not there, you can join using the same link. I will be there on 21st, Saturday 6 to 8 p.m.
21st.
Yes,
Week
21st is
pay,
Saturday.
yes, sir. Week pay link, sir.
21st Saturday 6 to
Yeah,
8.
link is same for all the weeks. So same link you can use. The link is always
Oh,
same.
okay.
Revision class what you said Saturday
6 to 8.
6 to 8. Na?
Yes.
We will revise the all syllabus. Huh?
Yes.
Thank you.
You will take questions from entire syllabus. You want only questions, right? Because in 2 hours there will
No.
be.
We will only discuss questions for all the weeks. Okay.
Okay.
Yes.
So you want assignment questions or all means other questions also?
Problem. We will revise. Assignment also will do. Not
Okay. Okay, so I will add all the questions. Means, different questions also.
What we will do, we will cover 120 questions, 120 questions at least. So we all will get good marks also.
Okay, so we'll try to cover all the concepts which are there in the 12 weeks. And yes, if we discuss all these concepts, then most likely you will easily pass through like that. Also, if you want, before exams, you can quickly go through all these slides. That also will be a further advantage for you because
Yes, sir.
these are summary of all the weeks. That also, so both will help you. That session also and these summary slides. then I think that will be sufficient.
Thank you.
So I hope.
Sir, small request, sir.
Yes, yes.
Sir, the assignment for assessment is not displayed, sir.
When assignment 4,
Yes, sir, the assignment for marks are not displayed in progress.
No, it is there, sir. It is showing up and down.
Okay, sir. Okay, right. Help you.
you can
Okay,
check
sir. Thank you, sir. Thank you.
once. No, sir. So are you able to see marks per assignment 4? Yes. Some of you are saying not showing, and some of you are saying showing. Marks are showing. So if some of you are saying that marks are visible, then I think marks should be available. Provided you have submitted on time.
So I submitted on time, sir. All the questions are also right in the at the quiz, but it's not showing in assessment.
Hmm. You can mail once you can mail them. If it is not, if that's the problem. You can mail them. They
The
will sort
problem with many, sir, also uh, asking this ask question.
discussion forum.
Yes, sir. So many are also asking.
I think they will resolve it.
Okay, sir. Okay, thank you.
So let us meet next Tuesday, 6 to 8 p.m. Thank you for joining.